Good morning. Today we'll start with the gas power cycles. We'll start with the Ericsson cycle. The TVS and PV diagram of Ericsson cycle are shown in figure above. So this is temperature entropy diagram for Ericsson cycle. This is pressure volume diagram for Ericsson cycle. In temperature entropy diagram, you can see the 1-2 process is heat addition at constant pressure, constant temperature. 2 to 3 is your heat expansion at constant pressure. 3 to 4 is your heat reaction at constant temperature, and 4 to 1 is your heat addition at constant pressure. The Ericsson cycle can be shown with the help of this diagram. So this is your Ericsson cycle where you had a compressor, turbine, and then you had a regenerator. So a steady flow system operating on Ericsson cycle. Here the isothermal expansion and compression process are executed in a compressor and a turbine respectively, and a counter flow heat exchanger serves as a regenerator. Hot and cold fluid streams enter the heat exchanger from the opposite ends, and heat transfer takes place between two streams. In the ideal case, the temperature difference between the two fluid streams does not exceed a differential amount at any point, and the cold fluid stream leaves the heat exchanger at inlet of the hot stream. So in the regenerator, the temperature of this stream start to decrease, and here the compressor outlet air temperature start to increase while the maintaining pressure constant. So this is a steady flow Ericsson engine. Both the Stirling and Ericsson cycles are totally reversible, as is the Carnot cycle, and thus according to the Carnot principle, all three cycles must have same thermal efficiency when operating between the same temperature limits. Efficiency of Stirling is equal to efficiency of Ericsson is equal to efficiency of Carnot is equal to 1 minus TL by TH. Stirling and Ericsson cycles are difficult to achieve in practice because involve heat transfer through a differential temperature difference in all components including regenerator. This would require providing indefinitely large surface areas for heat transfer or relying an infinitely long time for the process. Neither is practical. In reality, all heat transfer process takes place through a finite temperature difference. The regenerator does not have an efficiency of 100%, and the pressure loss in regenerator are considerable. Because of these limitations, both Stirling and Ericsson cycles have long been only of theoretical interest. However, Ford Motor Company, General Motors Corporation, has developed Stirling engines suitable for trucks, buses, and automobiles. So both Stirling and Ericsson engines are external combustion engines. That is, the fuel in these engines is burned outside the cylinder, as opposed to gasoline and diesel engine where the fuel is burned inside the cylinder. So external combustion engine offers several advantages. First, a variety of fuels can be used. Second, there is a more time for combustion, and the combustion process is more complete, which means less air pollution and more energy extraction from the fuel. Third, these engines operate on closed cycle, and thus the working fluid that has the most desirable characteristics, stable, chemically inert, high thermal conductivity, can be utilized as the working fluid. Hydrogen and helium are the two gases commonly employed in these engines. Despite the physical limitations and impracticals associated with them, both Stirling and Ericsson cycles give a strong message to the design engineer. Regeneration can increase efficiency. So it is no coincidence that modern gas turbine engine and steam power plant make extensive use of regeneration. So next we will start with the Brayton cycle, the ideal cycle for gas turbine engine. The Brayton cycle was first proposed by George Brayton for his use in reciprocating oil burning engine that he developed around 1870. Today it is used for gas turbine only, where both the compression and expansion process takes place in rotary machinery. Gas turbine usually operate in an open cycle as shown in figure. Fresh air ambient condition is drawn into the compressor where its temperature and pressure is raised. The high pressure air proceeds into the combustion chamber where the fuel is burned at constant pressure. The resulting high temperature gases then enter the turbine where they expand to atmospheric pressure while producing power. So the open cycle gas turbine and closed cycle are shown in figure. So this is our open cycle gas turbine cycle. You had fresh air will come into the compressor. It is compressed to high pressure. Then it will go to the combustion chamber where fuel is added, or you can say burning will take place at constant pressure. Then this will go to turbine where expansion and the exhaust gases will be ejected to the environment. This is open cycle. A closed cycle gas turbine engine is here. Your compressor, heat exchanger, heat is transferred to the gas, and then it is expanded in turbine, and after the gas heat is ejected to the environment. So this is a closed cycle. So there are total 4 processes. So 1 to 2 is your isentropic compression, 2 to 3 is your constant pressure heat addition, 3 to 4 is isotropic expansion, and 4 to 1 is constant pressure heat rejection. The TV and PVS diagram for ideal Brayton cycle are shown in figure. Note that all 4 processes of Brayton cycle are executed in steady flow devices, thus they should be analyzed as steady flow process. So when the change in kinetic and pressure energy are neglected, the energy balance for steady flow process can be, that is Q in minus Q out plus work in minus work out is equal to heat exit minus heat inlet. Now heat supplied in is equal to H3 minus H2 is equal to Cp T3 minus T2, and heat supplied out is equal to Q out is equal to H4 minus H1 is equal to Cp T4 minus T1. So efficiency of gas turbine with this Brayton cycle is that work net by Q in. So, or you can say 1 minus Q out by Q in. So Q out is given here, Q in is given here. When you divide, this will cancel out. So you have this efficiency in terms of temperature. Because of these two processes are isotropic, 1 to 2 and 3 to 4. So you can replace T2 by T1 in terms of pressure, P2 by P1, or T3 by T4 in terms of pressure, P3 by P4. As we know, P3 and P2 are equal and P4 and P1 are equal. So efficiency of Brayton cycle is 1 minus 1 by Rp raised to power K minus 1 by K, where Rp is the pressure ratio of the gas turbine, which is P2 by P1, or you can say compression pressure or expansion pressure ratio is the ratio K, and the K is the specificity ratio. So this is pressure ratio Rp and Brayton cycle efficiency. As you increase the pressure ratio, your efficiency of the cycle increase, and if further beyond 20, your efficiency starts to become a parallel to the x-axis, means there is a marginal increase in the efficiency. So this is the operation range from 5 bar to 20 bar, typical pressure ratios for gas turbine engines. The thermal efficiency increases with both these parameters, which is also the case for actual gas turbine. The highest temperature in the cycles occur at the end of combustion process, state 3, and it is limited by the maximum temperature that the turbine blades can withstand. Means this maximum temperature depends on turbine blades. This minimum temperature is the atmospheric temperature where your airlet went into turbine. So you can use different compression ratio varying from 11 to 16, but take this example here. This is a compression ratio 2. So here work obtained is this much amount. For compression ratio Rp say 8.2. This is 2 to 3, this is this 3 to 4 is your work output, and for compression ratio this Rp 15. After heat addition, this is the highest temperature attained, and this is your you can say work output. As you can see, for compressive gas we have to give some work. So this much amount of work is consumed here, this much 1 to 2 work is consumed here, and this much work is consumed here. So net worker, to obtain a maximum net amount of work, so you have to select a optimum pressure ratio, and here it is Rp is equal to 8.2. The criteria for maximum work output for two temperature limits is related by Rp is equal to T maximum by T minimum raised to power K by, divided by 2 into K minus 1, and so this is the optimum temperature range. Neither we can go for Rp is equal to 15, neither we can go for Rp pressure, low pressure ratio, neither too high. So there must be an optimum. The air in gas turbine performs two important functions. It supplies the necessary oxidant for the combustion of fuel, and it serves as a coolant to keep the temperature of various components within safe limits. The second function is accomplished by drawing in more air than is needed for the complete combustion of fuel. In gas turbine, an air-fuel mass ratio of 50 or above is not uncommon. Therefore, in cycle analysis, treating the combustion gases as air does not cause any appreciable error. Also, the mass flow rate through the turbine is greater than that through the compressor, the difference being equal to the mass flow rate of the fuel. Thus, assuming a constant mass flow rate throughout the cycle yields conservative results for open loop gas turbine engines. The major applications area of gas turbine is aircraft propulsion and electric power generation. The gas turbine cycle can also be executed for closed cycle for use in nuclear power plants. So this time the working fluid is not limited to air, and a gas with more desirable characteristics such as helium can be used. There is one more term which is called vac work ratio. So as part of the work turbine is used to run the compressor of the turbine. So because compressor will take, it is a work consuming device. So in gas turbine plants, the ratio of compressor work to turbine work, called the back work ratio, is very high, usually more than 1/2 of the turbine work output is used to drive the compressor. The situation is even worse when the isentropic efficiency of the compressor and turbine are low. This is quite in contrast to steam power plants where the back work ratio is only a few percent. This is not surprising, however, since a liquid is compressed in a steam power plant instead of a gas, and the steady flow work is proportional to the specific volume of the working fluid. A power plant with a high back ratio requires a larger turbine to provide the additional power requirements of the compressor. Therefore, the turbine used in gas turbine power plants are larger than those used in steam power plants of the same net power output. Development of gas turbines. The gas turbine was experienced phenomenal progress growth since its first successful development in 1930. There are different methods. Increasing the turbine inlet temperature. This has been primarily approach taken to improve gas turbine efficiency. The turbine inlet temperatures have increased steadily from 540 degrees Celsius in 1940 to 4025 degrees Celsius and even higher today. These increases were made possible by the development of new materials and the innovative cooling techniques for the critical components such as coating the turbine blades with ceramic layers and cooling the blades with the discharge air from the compressor. Maintaining high turbine inlet temperature with an air cooling technique requires the combustion temperature to be higher to compensate for the cooling effect of the cooling air. However, higher combustion temperature increases the NOx problem, means nitrogen oxide, which are responsible for the formation of ozone at a ground level and smoke. So, increasing the efficiency of turbo machinery components, the performance of early turbines suffered greatly from the inefficiencies of turbines and compressors. However, the advent of computers and advanced techniques for computer-aided design made it possible to design these components aerodynamically with minimum losses. Adding a modification to basic cycle, the simple cycle efficiency of early gas turbine were practically doubled by incorporating intercooling, regeneration or recuperation and reheating discussed in next two sections. These improvements of course come at the expense of increased initial and operational cost, and they cannot be justified unless the decrease in fuel cost offset the increase in other cost. So this is up to here is about the gas turbine cycle. Subscribe this channel, like this video, and thank you for watching this video.